And now this next you have two lectures. This is the world-leading expert, Christophe. Okay, I will not go much details about all this. If you can look at the web page about all these details, only I have to say that he is affiliated to the Ecole Polytechnique, Paris, and also the Omega groups who are developing all these high energy physics into electronics for many, many different devices. Okay, alpha, beta, gamma, delta, rock, at the end by rock, all was developed by their groups, and he is an expert of that. And recently, they are also affiliated with this different experiment, Atlas CMS. So you people know they are also now collaborating with us for this HGCAL detection. So without much word, I request Christophe to deliver his lecture.
Okay, thank you. Thanks a lot to the organizer for their kind invitation. I'm very happy to be here and share with you some insight in the front-end electronics that some of you will need to design. So the outline of the talk, so I will start with the example with low noise charge amplifiers and that are used a lot in many detectors, but with the example of pixel readout, and then say a few more words, then going to the example when we have now a large dynamic range, and so calorimeters, for example. I've been a calorimeter guy for a long time, so Atlas, liquid argon, now GCAL, and so on. So and then I will say in the second part more emphasis on the timing. So there is more and more things on the timing, and so I will explain the importance of the detector for the timing and the front-end electronics. What I should highlight is that the lecture is mostly for physicists, so I will not go into too many technical details, except if you ask, of course. So feel free to also ask questions if you need. So I'm available for you also during the breaks and anytime if you have also a specific question for your detector. So I will not go to really detailed engineering, explaining to you why this transistor has this size and this current and all this kind of detail. So there is also more slides than there is allocated time, so I will skip some of them. The good news also is that you don't need to know anything in principle to follow the lecture. The bad news is that usually students don't like electronics. I don't know why, but usually they don't like electronics. But okay, maybe it changes. I don't know if some of you like electronics this year. Oh, 3, 4, 5. Oh, much more than some of you actually work in electronics. Very high. Thanks again for the invitation. It's so refreshing to see the enthusiasm for electronics. Some of you actually work in electronics. Oh, one. Okay, so we'll have a beer together. Okay, now I say we'll have a beer together. I'm sure there will be 50 people working in electronics. Okay, there's a lot of electronics in experiments, as you probably have already seen a lot. And of course, coming from the detector to the reconstructing the energy and finding the Higgs and all of that, you need to, again, have all these electronics working. And the emphasis I will have again is what is the impact of the electronics on the detector performance, on the physics performance. Electronics, as you probably all know, has changed a lot. If you have a look from almost 50 years of high energy physics experiments, you would see that the detectors from outside, they more or less look the same. They have not changed so much, maybe a little bigger. The guy in front of Atlas here looks really small compared to the guy in front of Gargamel, but from outside, it has not changed so much. But of course, from inside, it has changed a lot, almost as the same thing from, this is for young people. This used to be the telephone you used to call someone. You probably don't know that. You have seen that in all movies. We used to be happy with that, but now, of course, you could not do so many things, and as you have seen, so this has changed so much. And this, of course, has impacted the way we do the physics. So we do the way, again, we reconstruct the events and we identify the particles that we get in our experiments. And so if you look again, the change in the readout electronics is really spectacular. Of course, not mentioning vacuum tubes, but the old board that you see in museum, and when you go now to integrated circuits, and in the event display, of course, then you see it a lot. I don't mention the bubble chambers, but the granularity that you have now here, and the speed of the electronics is really making you able to see things that you could not see before, just like that. So the Higgs could not have been found. It has been postulated 50 years ago, could not have been found without the progress in technology, whatever you would have liked. Okay, skip that one. I will speak a bit on ASICs. So this is application-specific integrated circuit. When you look in the web, you get a lot of advertisement for shoes. But so if you look for a particular chip something, you need to say electronic ASIC or the name. Again, this is putting transistors together in the same, on the same die. So this is the first one. You have two transistors here 60 years ago. Now you put millions of transistors, as you all know from your telephone, and we take advantage of that in the electronic, in the readout, and you will see quickly what we gained in having all the transistors together. The main thing is that now we're bringing the electronics inside, really on the detector, and this has changed a lot. You see it, of course, you have seen that last week, certainly, when you try to get the tracks from the charged particles. So you look at the tracker, the pixel detectors. It is, I'm just not using it to save the energy, but there are not so many things which are written. So I assume that you can just read the five, I think. Again, so measuring the charged particles, so you would not be able to do that. So without without the ASIC, so the ASIC have made possible this kind of detectors. Before we had wire chambers, and you could only read at the sides. So they are very high speed. There are millions of pixels. So millions of pixels. Your camera on your mobile phone, that's even more than that. It's so many pixels that takes too much space. Even you don't need 10 million pixels most of the time. Main difference with your camera here is that, of course, it works here at 40 megahertz. Camera sometimes, well, now they are more modern, but you need a bit more time. We'll mention things on radiation levels, and again, without electronics, you would not be able to do the track identification. One thing on calorimeter, so maybe you said it, I apologize, we arrived late, I had forgotten my passport at the hotel, so I will go back and so it's only 1 kilometer away, but it takes 15 minutes. So I'm sorry if you already said it and I repeat it. So when you look at the Higgs in gamma into photons, so the little blob that you see on the irreducible background, a large fraction of it comes from the electronics. So in the calorimeter resolution, you have the three terms, and one of them is due to electronics. And the second one, which is indirectly due to electronics, is the constant term. Some point you have many channels in your calorimeter. If you are not able to calibrate the different channels to a given accuracy, then your little blob will just wash away. And so there, the electronics is also coming into the play so that you can inject some signal and again, calibrate also your calorimeter properly. So Etienne showed the photons and single photon detection, and the little revolution that we had 30 years ago now, 20 years ago, silicon PM. So in the past, when you had few photons, you needed a photomultiplier to amplify on the different diodes the number of photoelectrons that you would get and get a sizable signal. The signal was just too small. With silicon PMs, and then we have some amplification just in the solid state device. It's almost the same revolution as we had going from vacuum tubes. If you open a very old television set, you would see that, or in a museum now, you would see that it was using vacuum tubes. So before transistor, people could already do electronics. They had radar, a lot of things. There was television before World War I. Well, no, so it's two, sorry, no, not World War II. there are still lesions. So there was already a lot of electronics, but again, the progress in the detector is also very important, and it's very important for those of you who will do electronics to follow very closely what's happening in the detectors. So we will see in the timing section, for example, that there is now a gain in the silicon detectors. We call that, for example, LGADs. There's SC LGAD. There are not a few detectors, and then at some point again, the performance of the detector, there will be a part coming from the electronics. And then this brings me to the overview of readout electronics. So most of the front ends, they follow a similar architecture. So we have nice detectors. Sometimes we have gain, a lot of gain, which means that we are not too demanding on the electronics performance, but sometimes we don't have so much gain, and then we have to amplify. As was said just before by Etienne, very often it's the first time when we just add noise to our signals. And so there we start degrading the signal to noise ratio and the performance. So we have to amplify the small signals that we get. And for that, very often we use charge preamplifiers. This is the case for pixel, for many detectors. This has been the case in the past for almost 90% of the readout of the particle physics detectors. We did not care so much on the shape of the current or the shape of the signal. What just mattered was the integral. How much charge did we get? Because the energy, the number of photons, what we wanted to measure was just proportional to the charge. So we just had to integrate the current. And so we used this thing that we call a charge amplifier. And we then measure the amplitude. Now with the increasing need in timing, then sometimes we need a little more to know about the shape, and at least we need more speed. And so I will show you tomorrow different architecture for the preamps. What has changed is changing all the time is the number of channels. So from hundreds to thousands, now you saw for the high granularity calorimeter, 6 million channels. This again has an impact on electronics, especially on the power dissipation. And now you have to do the same with low power. And so reducing the power that you put in each channel, because when you multiply by 1 million, every milliwatt is counting, obviously. So this is what the trend that we have in high energy physics, going to higher speed for the timing information, going to many channels. And so the trend is also for low power. Those of you who design or who have to use electronics, you have to make choices. And you could say that electronics design is very often the art of compromise. So from the physics requirements, you have a requirement on the readout electronics. So I said, for example, for the low noise, which is affecting the accuracy with which you measure your signal. Sometimes you will need high speed. And already these two parameters, and then you understood why you need to have low power, because we have so many channels and you don't like to bring pipes and cooling and all this kind of dead material. And already just on the beginning of this tree line, they are conflicting. When you need high speed, usually you need current. Why do you need current to go high speed? Because unfortunately, in many electronic devices, you have capacitor. And then if you want to change, at some point you have to vehiculate some information. Let's say I vehiculate the information as a voltage. Then if you want to change the voltage on a capacitor, you need the current. You need the current, which is just the capacitance times the dV over dt, something you learn in high school. And if now you want the dt to be very small, to do things which are fast, then the current will go up. And the only way you will bring the power down will be to bring the voltage down. This is why the logic levels, they have gone down. The TTL used to be 5 volts. Now people do logic with 1 volt. And the other thing they do is capacitance. And so this is why all the electronics that you are using is improving so much, because capacitance with the technology shrinking, I'll say a word on that, is bringing down the capacitance. And so this is, for example, the way of finding the compromise between these conflicting requirements. First thing you need to do when you have to design readout electronics is, of course, to modelize electrically the detector. you have your pixel, you have your silicon PM, you have your photomultiplier, you have whatever detector you have, and you need to make an electrical model to convert the quantity that you will need to measure, the charge, the current, and be able to see what you need as an electronics device to handle this information. In high energy physics, we are a bit lucky for the electronics that the detector modelization is more or less always the same. So it's a current source, and most of the detectors, they are purely capacitive. So you have a junction in which you create charges with the ionizing particles. And so then you have high voltage. Without high voltage, it would not work. With the high voltage, the charges are moving. The movement of charges is the definition of the electrical current. So you have a current source, and your detector is just, again, electrode or a doped region in semiconductor. And so the impedance of that is really something which is capacitive. So most of the calculation we do and the modelization that we do for the front-end electronics is using this simple model for the detector. What is changing, of course, a lot is the value of the capacitance. If you go into pixels, so this or strips, you go even below that 0.1 picofarad. So 3D pixel, they would be now more in the 20, 30 femtofarad region. If you have strips, of course, you have more area, and so the capacitance goes higher, but you are speaking of picofarads. Photomultipliers is also very small, maybe 10 picofarad. Silicon PMs, as was shown, so you have many of these Geiger cells put in parallel to be able to see many photons. And so there you are more in the hundreds of picofarads. If you go to the big calorimeter, so this is the Atlas liquid argon, this is more 100, 1 nanofarad sometimes, so you go to very hard, large values. Of course, sometimes the modelization needs to be a little more complicated. For example, when we studied the liquid argon calorimeter, there was an accordion shape. This is something which is already 50 centimeters long. So the propagation time is already something like, I don't know, 5 nanoseconds in the calorimeter, a few nanoseconds in the calorimeter. And so if you want to measure timing or things like that, you have to wonder whether this thing looks like a transmission line or a capacitance. And sometimes that you have to put into an account. As I said, the signal is usually the movement of charges in an electric field. And so this is the definition of a current source. And so the signal is represented most of the time as a current source here. So an ideal current source, this is something which has an infinite impedance. What does it mean? It means that the current here will not depend on the voltage. The impedance is the ratio of the variation in voltage to the variation in current. And here the current does not vary. So you have delta I is 0. And so then the impedance is infinite. And so this thing has an infinite impedance, and which is a nice thing. It will not depend on the voltage that you will put on your electronics. For a very long time, as I told you at the beginning, we have modelized that as simply as we could. So it's an infinitely short pulse. We don't care whether it's 1 nanosecond, 0.5, 2, whatever. We modelize that as an infinite short pulse, so current, and we only know the integral, and the integral is the charge that we want to measure. And so this is why we have this, what we call Dirac or impulse modelization for the current source. Of course, once again, when we do that, we are a bit too simple. We are omitting many things that make that usually when people speak of electronics, they speak of problems. Problems with my electronics, and so on. A lot of your problem will, of course, come from what is missing in my picture here. The first one, which is here, the high voltage, so nice source to inject noise. The high voltage, almost perfectly coupled to the preamp input, a royal path for noise. At some point, there is some high voltage here. There are connections, connectors, parasitic inductance, grounding issues, lots of things I will not talk about, but if you work in electronics, you will have to face this kind of thing. We'll say a few more words after that. No, it's not on that one. Again, just very, very shortly, sometimes this is too simple. And for example, when you are interested in timing parasitic inductance that you may have, you may remember that typically the inductance is 1 nanohenry per millimeter. So as soon as you have a little wire of 1 millimeter, you have what, I don't know, in inches, this is 0.0, Americans, UK people. In India, you are using kilometers and millimeters and things like that, I think, not inches. Okay, so I don't need to convert it into inches. Few nanohenries. So you see, just going from the last dimer to the output, so this is a few centimeters. This is already 10 nanohenries. If you're slow, you don't care. If you now look for high speed, this is going to hurt. You cannot vary quickly the current in an inductor. As you know, this is Lenz's law. And so this thing will oppose the di over dt. So if you want to bring the current out quickly, this thing will oppose to that. And so it will be difficult to have very high speed when you get parasitic inductance. And so this is something you will have to struggle with if you do timing. Again, sometimes I will not go into detail. So silicon photomultipliers we use a lot. And so then you have to make the model for the signal a little more elaborate, quenching resistor, parasitic capacitance, and all the pixels which have nothing that are still there just to make the impedance. Now we would like, as I said at the beginning, so this first lecture is we would like to measure the charge. Tomorrow we would like to measure the time. So today we measure the charge, we don't care about the time. Reading the signal, so if I ask you, how can I get the charge from this current source, you will tell me it's a piece of cake. Because this is a capacitor, the capacitor is integrated the current, and so the voltage here is just proportional to the charge. This is the voltage here is Q over C, this is again high school stuff. So just measure the voltage here and you get the charge. But true, this is what can be done, so it's very simple. Now we can say, what is the gain? Well, for purists, a gain is something which is dimensionless. It's a ratio of two identical dimensions. So speaking of gain, when you get voltage, the ratio of picocoulombs on picofarads is not dimensionless. So it has a strange unit, but whatever, we can call that gain. If you have 1 femtocoulomb, which is again the typical chart that we get, for example, from pixel detectors or for many detectors, we speak in femtocoulombs. Sometimes we even speak in electrons. Femtocoulomb, a few thousand of electrons. You see on 1 picofarad, I get 1 millivolt per femtocoulomb. This is not so much. If you want now to measure that precisely. So, for example, for a pixel detector, you want to see whether you got a hit or not. Then you have to see, is 1 millivolt a 0 or a 1? Remember at the beginning, I told you on the digital electronics, we are happy because we came from 5 volts, which was a 1, to 1 volt. So now in your telephone, whatever, a 1 is 0.8, roughly 1 volt, not much less. 0 is something around 0 volt. 1 millivolt for the digital guys, no question asked. This is a 0. No way to see that this is a 1. So this you will need really to amplify just to make a digital signal. Calorimeter guys, then they like to measure from MEV to TV or that kind of this kind of range. So at some point, if you don't want to bring out kilovolts for TV, it means that your minimum signal is less than millivolts. And so in the calorimetry, 1 millivolt is already a lot. So depending on what you want to do, it's a lot or it's not. But whatever is there, you get your voltage Q over C. Now you need to do something with this voltage. You need to connect something here to be able to use this voltage that you get here. The minimum that you can do would be just to use a buffer. So this thing, again, is something that I'm sure most of you have already studied in the past. So this is an op-amp which is connected, we say, as a follower. So this is copying the voltage on the input here to the output. And so the main advantage of this thing, so they are perfectly identical, thanks to the open loop gain. And the main thing that it does, that the input impedance here is infinite. So you put the infinity in parallel to that, so it changes nothing. But the output impedance is 0. So now you get a perfect voltage here. This is something, whatever you connect, the voltage will never change. This is like battery in your car, even better. Whatever the current you ask, whether you start the answer, the voltage stays there because the impedance is very low. So this is what we call in electronics a voltage source. So this thing is making what you want. Now you can connect whatever you like here. You can use the signal because now you have sort of separated the input to the output. With an ideal amplifier that you studied when you were young, this works perfectly. Now when we come to the real world, this thing is not an infinite impedance here. There is minimum a little bit of capacitance, parasitic capacitance. If you buy an op-amp, if you just use an op-amp that you find in the drawer in the electronics workshop, this will be picofarads. So you're already degrading your 1 picofarad here by several picofarad. You are losing your 1 millivolt is going down to a fraction of millivolt. If you want to read even smaller capacitance, then this kind of thing is completely out. So you need this thing. I will say a word on that. You may have crosstalk. I will not talk about that, but we can talk it at the break if you need. And lots of things which are interesting and I will not talk about. At some point, the charge is coming in, gets integrated in the capacitance. Then the next event comes and gets on top of the first one. And then this thing just goes up. And at some point, you need to remove the charge just to restart from the baseline. And so at some point, this you will have in all the amplifiers, you will need to drain the charge away from the capacitor. So this is something that is actually used. So it's used in your telephone now in the monolithic active, in what we call CMOS cameras. In our field of high energy physics, we have what we call maps. So I think this was already presented last week, probably. So monolithic active pixel sensor. We exactly use this characteristic. And I said at the beginning that I would not show you transistors. I lied. I'm sorry. There are 3 here. But I will not go into all the details of transistor. I show them so that you are not afraid of looking at a schematic with transistor. There are only 3 transistors here, and there is only one really doing the work. So it's really something simple. The one doing this work is this one. And this one is exactly the same thing as this. So this is what we call a common drain for the guy doing electronics. So this is a common drain configuration. This is high impedance, this is low impedance. This thing is just copying the voltage. The advantage that we have when we have just one transistor is that the parasitic capacitance that we add here is minimum. The 2 other transistors, this one is doing exactly what I said. It's easy to see. It's called reset. So at some point, it's getting rid of the charge, which came at the beginning. So this one is like a switch when you switch on the light here. You reset, so you short circuit this thing, you drain away the charge, and you're ready to take the next one. This one is also a switch. It's something that when you have millions of pixels, you cannot read all of them at the same time. And then you read them usually sequentially, usually by column. And so this is just bringing, we said this is a voltage, and we bring this voltage at the bottom of the chip. Then we convert this voltage into bits. We have what we call an NADC here. And so this is a switch to say, the pixel number 1, send your voltage, then pixel number 2, then pixel number 3, and so on and so forth. So this is all that these transistors are doing. So we have these in high energy physics, in maps. So there we collect the charge by diffusion. So I will not go into the details. Just a few comments on that. So this thing only came up 10 years ago. Why not before? As you see again, schematic is not very complicated. You understand all these three transistors, why they are here. Why didn't we do that before? Reason is simple, because before, these transistors, I told you at the beginning, was already picofarads. The charge that we get by diffusion is a small fraction of femtocoulomb. This was not just enough. What has happened in the last 10 years, as you have seen, there is Moore's law. There are slides in the backup on that. As you all know, so the technology is getting smaller and thinner. And now the capacitor here is, I don't know, 10 femtofarad, something like that. So we have improved by so many orders of magnitude these capacitance, that things which were not possible in the past now get possible. Just the message here is that when things change, you have to keep your mind open. Things which are not possible, sometimes they become possible. So this kind of architecture we could have not have had in the past, but then things are changing, and then we can revisit things like that. Okay, I cannot go into too many details if I want to talk to you about electronics noise at the end, just before the lunch, so that and so I will come now to the charge preamplifier, and of course I will start with the ideal charge preamplifier. So at the beginning we said, okay, we need to put a buffer to copy this voltage. So at some point we need a kind of amplifier or whatever. Once you have an amplifier and you say the voltage I get here is not so much, you would say, why not use the amplifier to amplify this voltage rather than just copying it? And so this is what people are doing. And so they use this amplifier. And so there are many ways. So we could have gone through different possible architecture. We are going to use here. So this is once again for the guy who has studied electronics, what we call shunt feedback. We are doing a configuration. This is also in the backup slide, if you want really to know there are only 4 feedback configurations. There are 3 quarks, but there are 4 feedback configurations. You can look in the slide, and one of them is converting a current into a voltage. In electronics, we call that transimpedance, okay? And so there's only one, which is converting. You put something between the input and the output, and then you convert a voltage in a current into a voltage. This is exactly what you were asking. Your signal is a current source. I want a voltage. Then I use the shunt feedback. Now, when you do that, if you put a general impedance here, G, here, your voltage would be your current times your impedance here. And then you remember that, oh, I also want to integrate my current because I want the charge. I just don't want the copy of the current. I want the integral of the current. So I want something that integrates. This is called a capacitor. And so I put a capacitor in my feedback here, and then I get what is called commonly, for 50 years now, a charge preamplifier. And so what we call the charge-sensitive preamplifier is this thing. So it's an amplifier, whatever amplifier, with capacitance in the feedback. Now, during your long evenings, when you don't know what to do, you will do the little calculation in which you say, what is the output voltage when I know the current. So you have two small equations that you can write here. One saying that the current will go two ways. One part will go on the capacitance. The second part will go into the amplifier. We suppose that there is no current going inside the amplifier. This is a perfect ideal amplifier. So the impedance of the amplifier is infinite. If it's not, then it comes in parallel with CD and the same calculation. And so as the current is not going here, it's going into C sub F. This is just what is written here. The current goes two parts, one in CD, one in CF. And then we remember that this thing is an amplifier, which means that the output voltage is proportional to the differential input voltage. This is what is written here. You just reshuffle this thing, and you will find this famous transimpedance is 1 over J omega CF. So this is the impedance of the feedback. There is a little term here which depends on the actual gain of the amplifier, but usually the gain is very large. So an ideal amplifier with an infinite gain, and so this term here would be 0. When the gain is not infinite, this is what in electronics we call ballistic deficit. So sometimes we'll find something, it's the charge that we cannot completely extract from the sensor and which stays on the sensor. Again, usually it's very small. We make sure that this thing is small enough. Again, once I neglect this term, my transimpedance is minus 1 over J omega CF. So this is this is in frequency, so you may not like so much the frequency approach. So you can go in the time domain by the inverse Fourier transform. You go into the time domain. So now this is the output voltage as a function of time. 1 over CF, this is a constant, times the current, divided by 1 over J omega. And you remember that 1 over J omega is the integral in the Fourier domain, which means that the output voltage is the integral of the input current divided by CF. So it's similar formula, except that now we have a low impedance here, so we can connect anything we like. We can choose CF as we wish, which means that when CD is large here, you don't get much gain here, but here you can make CF very small. So in the pixel, for example, we use C sub F, 10 femtofarad, 20 femtofarad, so that we get quite some amplification here. So now your gain is completely independent of the choice of the capacitance. So again, instead of integrating on C sub D, we integrate on C sub F. So this is simple. This is insensitive to the preamp capacitance. Once again, it integrates something. For a very long time, this was very useful. So the output voltage was just proportional to the charge divided by C sub F, and it was staying there for a long time. When the ADCs were slow, you had plenty of time to digitize. Moreover, you did not care exactly when the signal arrived or when you need to digitize. Here, you can digitize anytime, you will get the correct value. So this was very, very comfortable. So this is 90% of particle physics detector, and usually I will show something tomorrow. This is built with a custom circuits. A few words. No. Well, a few words in advance on a little bit of timing. So I told you that we were just interested by measuring the charge. So this is the voltage at the output of this thing. If you look at this here, it looks infinitely fast. Actually, if you use a real amplifier, you will see that it's never infinitely fast. And as you can imagine, at some point, the speed of the amplifier will come somewhere in the speed on the output. And if you just open a data book of op-amps, you will find 1 megahertz amplifier, 1 gigahertz amplifier. You will see that, of course, you can buy amplifier with different speeds. And so the speed of the amplifier at some point will affect the shape of the signal at the output. But where can it intervene? The calculation that we did here is very general. We did not suppose anything on the amplifier. At some point, it will intervene in the fact that the gain here is not something which is constant. And so when you buy an op amp, if you buy a 100 megahertz op amp, what does it mean? It means that if you go higher than 100 megahertz, you have no more gain. This is what you see when you buy an op amp. This is a 200 megahertz op amp, right? An old one. So you see that the gain, so when you buy an op amp, usually it has a high gain. What people don't tell you is that it's the gain at low frequency. So it's what you see here, 60 dB, 1000. So at low frequency, you amplify by 1000. But at some point, there are, again, parasitic capacitors inside the amplifiers, which will make that the gain will start decreasing linearly with frequency. So this reminds you the impedance of a capacitor. This is exactly the reason why the gain is decreasing. And at some point, you have no more gain. And so this is what we call the unity bandwidth, so the open loop gain bandwidth of the amplifier. And so the modelization of the amplifier is relatively simple, what's called in electronics the first order. It means that the gain is decreasing past this frequency here, linearly with frequency. This is something that you see pretty well here, and that you can find also tomorrow. We will find it also in calculation. So now we have an expression for the gain, and so you can replace this expression into the one that we calculated on the previous slide. And when you do that, you find that now your transimpedance is still this integration, but now you have a second term which is depending on frequency. So you have to go back into again your Fourier transform to remember that this in the Fourier domain, in the frequency domain, is the equivalent of a rising exponential. I'm sure you have done that many times in your courses, And so you find a rising exponential, and the rising time constant is given by this value, CD, G0, and CF. This is the time constant of this rising exponential. So now it depends on the sensor capacitance. So the larger the sensor capacitance is, the slower will be your rise time. This you would expect. It depends also on the speed of your amplifier. So if you use a fast amplifier, omega 0 G0 will be large. And as you expect, this time constant will be small. And something that you probably not expect naively, it will depend also on C sub F. And so if you choose a feedback capacitor which is too small, it will slow down your amplifier. This is the electronics way of saying there is no free lunch. You get a lot of gain, you pay with the speed. Okay? And so if you want to be fast, you will not be able to have a lot of gain at the same time. You will have to choose. And usually, again, this is tomorrow in advance, when you want to be fast, then you limit the gain, and then you cascade several stages, but with less gain. This is the way you get a lot of gain. To move on, I'm a bit so sorry. I'm sorry, usually this lecture is in 1 hour and a half. And so then we have shortened a little bit. So sometimes you may find and things may go a little fast. For example, on this one, I will go very fast. I will not go into the detail. I will just calculate one thing, which is the input impedance of the amplifier. Then you would need to go to do the calculation. I do it for you. You will find that it's very, again, general. It's the feedback divided by the gain. What does it mean in practice? When the gain is very large here, if it goes to infinity, it means that the input impedance goes to 0. The electronic guys, they call that a virtual ground. It means that this is the same as ground. So if I go back to, no, on this one. If I go back on this one, sorry. It's another way of saying that the voltage here does not change. This is down. Again, when you were probably younger, you would say that the two inputs would be the same here. And so if we have this configuration, you will get 0 volt here. This is only true depending on the gain. And as you have seen, the gain depends on frequency. So this will only be true at low frequency. And the frequency will go up. This will stop to be true. the gain, the voltage here is 0. This is why we call that a virtual ground. It's not a real ground. We have not made a short circuit, but it means that the voltage here will not vary. And this has nice properties. By the way, this is the reason why all the current is going into the amplifier. It looks like a short circuit. It looks like ground here. So the current goes to ground. It's a low impedance here. This is why in this formula, you were not sensitive on C sub D. If everything goes in the amplifier, nothing goes on CD. Another way of seeing it is that, again, if there is no voltage variation on CD, there is no current going into CD in this term here. It's cool. One nice property of that, again, you are not sensitive to the sensor impedance, and this is why you don't see so much if you connect other things to your input. It will not affect your response. And something that you don't connect, but which gets connected anyway, is neighbors. You have capacitance to neighbors. That's called crosstalk in electronics. In real life, you have neighbors. It's called usually a nuisance, but in electronics, very often neighbors, or sometimes you have nice neighbors. But in electronics, it's also something that you get signal into the neighbors, and then you can have many channels, for example, triggering. If the voltage on the input does not change, you cannot have current going into the neighbors. I skip the input impedance with a real pump. You can do the exercise. And so this is just what I said on the crosstalk. This one, of course, I skip. And I come in the last 10 minutes on the electronics noise. And of course, I will not give you a full lecture on the electronics noise in 10 minutes, especially just before lunch. I will just go into what you need to know for the noise. So what's going to affect your performance? And how will you be able to calculate the noise that you're going to get at your preamp output? Interesting. So this is a real measurement. And so this is a signal that you have on your preamp output, on your system output. And you see that, of course, you measure the amplitude here. It's proportional to the charge, as I said at the beginning. It's not exactly like your preamp. It should have stayed flat here. So I'm anticipating a little bit on noise. So let's say I discharge the feedback capacitance so that we are able to read a second even after that. It's the same preamp. And I don't know if you can see that on the red one, if you measure the amplitude, so the real amplitude is 5 millivolts here. If you measure here, you are wrong by almost a factor of 2 because of the noise. So you see that this fluctuation on the preamp voltage output is due to electronics noise, is immediately affecting your measurement. I don't know if you see what's different between the red one and the blue one. It's the same electronics. There is only one thing which has changed. The one electronics guy, you should come on the first rank tomorrow. Well, you can see it's the speed. In electronics, we call that bandwidth. The blue one is slower than the red one. And so you see immediately that one thing which affects the electronics noise a lot will be the speed, the bandwidth. Here, I'm something like 3 times faster than on the blue one, on the red one. And so I've increased the noise quite a lot. You see on the blue one, I still get noise. This is something which is not so negligible. So there are 3 types of noise: fundamental noise, the thermal noise, shot noise, excess noise I will not talk about. And then in real life, what you will fight about and what you were mentioning is all this noise, ground loose, well, all this thing. And again, we could have a full hour just on this last topic, but I will skip that one, of course. So we need to be able to calculate. So the goal of what I'm going to do now in 10 minutes is try to see how can I calculate the amount of noise I will get on top of my signal. So I will need to use a few things. I will need to use some modelization. And in electronics, we can show that we can modelized noise generators. I will say that at the beginning. So it's like adding something during the noise. But of course, we don't have the expression of the noise as a function of time, because if we knew that, we say, oh, we are going to have a lot of noise here, so I need to subtract the noise, and this would not be something which is random. The only thing that we know is what we call the noise spectral density, so the power of the noise. So that's to be practical. So how much power do we have for noise? And the formal definition is, again, the module square of the Fourier transform of this generator. So you're going to tell me what I'm going to do with that. Well, we are going to make the calculations. So it means that we will be able to calculate what we call the noise spectrum in the frequency domain. And then we are going to use a very powerful theorem, which is called Perceval's theorem, or Wiener-Khinchin theorem in a more general way, which is just saying you that the power in the frequency domain, so the integral of all the frequencies of the noise density, is the same than in the time domain. So it's a very general mathematical theorem here. And this thing here is just what we call RMS noise. So this is the variance of your generator. So if I know the variance of this thing, I can make an histogram and I will know this, what we call RMS noise here. I will know the amount of noise which I get. So you see that if I know these two generators in the frequency domain, I will be able to know the noise that I will have at the output of my preamp. So this is the same preamp as before, but now without the signal. And so you see again this fluctuation of the output voltage. I will go quickly once again. This is my preamplifier. The electronic component, they are generating noise. So this is a very fundamental notion. There are many components inside my amplifier, so it's a bit painful to do all the calculation. And we are saved by one thing, which is saying that it's the superposition theorem, saying that I have many generators in that, but I can bring all of them into just two generators on the input. And if you talk to the electronics guy, they will talk about their series noise and their parallel noise. And so this is these two generators. There is one in series, which is a voltage one, and there is one which is a current one, which is in parallel. So the term of series noise and parallel noise, this is just another way of saying voltage noise, current noise. You need two generators to put all these sources of noise at the input of a noiseless preamplifier. This is because it will depend on what is connected in front of that. And once again, you can see that just empirically easily. If I connect to nothing, then this noise generator cannot draw any current. It's like just plugging one wire into your plug. There is no current return. There is no current that can flow. So if you have an infinite impedance, you will never see the series noise. I can go the other way. You like, of course, extremes. If I know my sensor impedance here is a short circuit, so I connect here to 0. So now I will see a lot the series noise. But this parallel noise will be short-circuited. So I will not see any parallel noise. And so you see already that depending on the impedance, the amount of series noise and parallel noise will be different. And so again, a low impedance sensor, you will see more the series noise, and a high impedance sensor, you will see more the parallel noise. But you remember at the beginning, I told you my sensor impedance is the capacitance. And so now low and high impedance doesn't mean anything because it will depend. Capacitance is an infinite impedance for zero frequency, for DC. But if you go to very high frequency, this is now a low impedance. So the impedance just goes as the inverse of the frequency. So this is one other way of seeing that the series noise, you will see more when you work at high frequency than when you work at low frequency. Just now going into the calculation. So this is the most difficult slide of the full lecture of electronics today and tomorrow. I will, of course, not go into the calculation because I don't have the time, but you are students, so you have plenty of time, and encourage you to do the calculation. It's not so difficult, so I will do the one for this one, which is an easy one. So this generator is the same as the signal. And you remember that I'm looking what is the voltage due to these generators. And for current, I just multiply this thing by my feedback here. So this is why the output is my current times my feedback module square. This one is a little more difficult. You need to know what current this voltage generator is sending into the preamp. And as I said at the beginning, this will depend on the impedance on this side. The current will be proportional to, inversely proportional to this impedance. If you calculate the current that is due to this noise generator, is this one divided by, again, this impedance here. So you see that you get an expression which is not so complicated. And if you now assume that you have a capacitive sensor here, charge amplifier, so you will see, you will get this kind of expression, and you will see that the series noise is flat as a function of frequency, and the parallel noise is going up with low frequency. We are finding again the fact that at high frequency, you see more of the series noise, and at low frequency, you see more, you are more sensitive to parallel noise. It's exactly the same. I'm almost finished because what we would like to know is, again, the RMS noise, so the integral of this thing. You are young, so you love to calculate integral, I'm sure. But immediately you see that this integral is diverging both ways. This one is diverging on 0, and this one is diverging on infinity. This is actually not in a, so in an ideal amplifier, this is what you find. In a real amplifier, this is not what you will find, and the integral will not be diverging, because at some point we see at the beginning, the amplifier is not infinitely fast. It means that the high frequencies, they get cut at some point. This one means at some point, you need again to discharge CF. The other thing that you can see is that you will get a lot of noise. How to reduce the noise? We do what we call shaping. And shaping, meaning this thing, we have a lot of noise at high frequency. I need to use what in electronics we call the low pass filter, something which is removing the high frequency. It's something that slows down the signal. So you remember at the beginning, we saw between the blue one and the red one, the blue one was slower. So this is what we did here. We cut the high frequency. We also cut the low frequency to reduce the parallel noise. This was the fact that the signal was going back down and not staying up. And so this is what we did on the plot that you showed before. We did a little bit of shaping. On your signal, this is what the shaping is doing. So it's slowing down the pulse, and now it's coming back. In 1 minute, I will now bring that into the way of expressing the noise. So we have expressed the output noise, the RMS noise. What is more interesting, of course, is the signal to noise ratio. And in electronics, for unknown reasons, people, they do a noise to signal ratio. Don't ask me why, this is what they do. So they say, I measure charge. I can calculate the noise in millivolts at my preamp output, but I don't like millivolts because I'm measuring femtocoulombs. And I would like to know these millivolts, how many femtocoulombs does it correspond? Something which is easy because we know that the gain of the amplifier is 1/CF. So when we know the voltage at the output, we can bring that into femtocoulombs on the input just by knowing the feedback. And so this is what people call the equivalent noise charge. And of course, you can find that it will depend on the shaping that you are using. So this shaping time constant and the series noise and the parallel noise, they will behave differently. So this calculation that you can do. And you see that when you do fast shaping, the series noise is increasing. When you go slow shaping, parallel noise increasing, and you see that there is an optimum, which you could see here already. You see that on this thing, you will get an optimum. And this is where people in the past used to work. maybe, I don't know if I want to finish just on that one. So I will finish on that one, but just by saying that if you have no other constraint, you will work at that point. So this is kind of realistic figures here. You come back to more on that. You get something like, I don't know, 70 electrons, whatever, and at shaping of a few hundred nanoseconds. If you want to work now faster than that, for example, for LHC, we work more in the 20 nanosecond region, which is here. And you see immediately that you don't care on the parallel noise. Whatever you do, you are now at high frequency. And so this is other constraint which determine the shaping that you are doing. So you try, of course, not to be too fast, but this is where sometimes you will work there because of the pilot. Okay. And so this is how you can, again, see the price you pay for having fast electronics. So you see that from the optimum here at 70 electrons to LHC-like shaping, you have worsened the noise by a factor of 3. It would be very difficult to regain this factor of 3 just by electronics. I guess, sorry, I have a bit of a time. I tried to squeeze as much as I could, but it's.
Thank you, Christophe. Before starting the question, I just say, Christophe, this shaping circuit by amplifier, charge sensitive amplifier, those are in our experiment. They are doing the experiments.
They are
now we can apply what you taught. They will understand much better way. Yeah. So the question.
Yes.
Yeah,
Yes. So while trying to get a high gain, there is a cascade of preamplifiers. So my question is the preamplifiers the same schematic repeated over and over, or do you have different amplifiers at each stage?
So the gain of the amplifier, the only thing which was important, I did not assume anything on the gain. We could go in more detail at some point. What was important is that the gain times the feedback capacitance would be large compared to the sensor capacitance. So this is all that we ask on the gain. If we go into more details, then you would see, I did not talk about it, that the gain, what we call feedback. So the fact that we have a feedback element, we are improving the linearity of the response. And so when you have more gain, then you can improve the linearity and you improve the overall response. But we don't rely so much on the value of the gain. It's not a main parameter. Yeah.
Hello, sir. So these days we have very fast FPGAs where we can do digital signal processing. So I want to know the basic differences between this analog signal processing and digital signal processing, and why, which one is better for our purpose?
Yeah, thank you a lot for this question. Indeed, this is here what we call here, I should put it here. This is analog shaping. So I did not mention it. We call it, for example, CRRC. So this is just because a resistor and a capacitor is a low pass filter and it's a RC, and a capacitor in series with a resistor is a high pass, and we call that a CR. And indeed, this is just, I could have drawn it on the blackboard. So this is some analog filtering. And once you have chosen R and C, they are what they are. And if at some point, for example, this part can be due to the leakage current in your sensor. This is something that is going to change. For example, when your sensor gets irradiated, if the temperature goes up or whatever. So this thing is going to increase and your optimum will no longer be your optimum. And so it's something that you don't like so much because of it's not adaptable. And as you are rightfully pointing out, you can also do that with digital filtering. I should have a slide. No, it may be in the backup, but if you take samples on the waveform, you can, by combining the different samples, you can do the equivalent of filtering. You can do even better. You can do what we call non-causal filters. And so it gives a lot of flexibility because when you change the coefficients you put on the waveform, then you can move this, what we call here, the central frequency of the shape of the optimum shaping time. And so indeed, this is something which is done a lot. For example, Atlas was calling that multiple sampling. So they are taking 5 samples on the waveform and they are combining them. So for example, when the luminosity is changing, they change their coefficient. And so they move this thing as a function of frequency. I don't want to be too long. You cannot do everything. And so there's always a tendency. So sometimes people will tell you everything should be digital. At some point, you have to be careful on one thing. And this comes also in the timing thing. When you're, if you are not limiting the bandwidth here, it means that all your samples will have more noise. You will be taking samples without any filtering, which means that you will have more noise, so you will reduce the noise, but you will start from a higher noise. And so at some point, we need to do a sort of catching off the unnecessary noise, and it's called also very often anti-aliasing filtering. So you remove the high frequency so that you don't have too much noise on your samples, and then you do digital filtering to get the flexibility. Yeah, all the experiments now they do it. Yeah, it's very important.
Okay. Any more questions from students? Yeah, those who are the instructor of this experimentation.
So I have a very basic question. What do we mean when we say there is a bandwidth limitation in our detectors which affect our rate handling capacity? So how does it physically mean? What is the bandwidth?
Okay, it's not a short question, so thank you. It's probably more a question for tomorrow, because tomorrow we will work on the timing, and so we will look a lot on these bandwidth issues.
Okay,
Just one word before tomorrow, you see that the sensor itself, there is no, well, except from sometimes the physics process. So scintillation light, you saw from Etienne, that I will probably not put it in the correct way and you will correct me, but, from getting the first photon and then getting the photons out of this, there are many processors in cascade. And so this is sometimes affecting the bandwidth. Tomorrow, we will see that, for example, I will take an example which I know better, which is, for example, pixel silicon detectors. There is the mobility of your carriers inside your junction. And at some point, they take a certain time to cross the junction. So this is the current duration. So we will talk a lot about that tomorrow. And so this is already limiting the bandwidth of your signal. So I will say a lot, and the rest will come from the electronics. Tomorrow, you will have a lot more on that.
Okay, with that note, we close this session today, and tomorrow we will be again. And as I mentioned, today is a long, you have a long session. And now the lunch and then start. Thank you, sir.
Yeah, we